this unit we've looked at solubility, and we've looked at weak acids and strong acids, weak bases and strong bases. All of the stuff with acids and bases is going to be important when we look at things called titration curves. And a titration curve is showing us on a graph what's happening to the pH when an acid and a base react. And there are some really important zones or values in this that I've identified on our little sketch here. So this looks a bit messy at the moment, so I'm going to sort of walk you through it. The first thing is I've actually shown a reaction where I've started with a weak acid and I've reacted it with a strong base. I know that because I've learnt the general shapes of those. And if you're using our current textbook, the general shapes for those are on page 197, which I've put up here. Okay, so one of the things you have to do is recognise the general shapes so that you know what you actually start with and what you end and what it was being reacted with. A typical example for this one would be sodium hydroxide being added to ethanoic acid. Okay? The things you have to be able to calculate are as follows. You have to be able to calculate the initial pH of whatever you start with. You need to be able to calculate the final pH after it's been completely reacted and you've got excess of, in this case, the strong base. You have to be able to work out the pH and the volume for what we call the equivalence point. This is actually quite tricky. Okay, and this is one of the things that we'll show you next term. You have to be able to calculate the pH and the volume for the half equivalence point, which means where there's just as much acid as there is conjugate base, and so it's what we call a buffer region. This is actually incredibly easy. Ethanoic acid has got a pKa of 4.76. Therefore, I know that this value here is at a pH of 4.76, regardless of the concentration of it. I also know that this is going to be half of this volume here. So when I've worked this out, I just halve it and I get this one. Hence its name, half equivalence point. And the last thing we have to identify is the buffer region, which is actually probably the easiest thing to do. If you know the pKa, 4.76, this goes from 3.76 to 5.76. It's the pKa plus or minus 1. So it's actually really easy. What we're going to spend a lot of time on next term is how to calculate region 3, which is the pH of the equivalence point, and therefore that will help us get the volume for the half equivalence point. So those are the two things we're going to really worry about. We're also going to use the calculations in this to analyse things called buffers, which is a special type of chemical where a conjugate acid and base pair are both present, weak acid-base pair are both present, so that it can control its own pH using the Chatelier's principle. But what I want to look at today, just very quickly, is to tell you how do I find number 1 and number 2. Once I know the shapes, then I know if I've started with a strong acid or a strong base, or a weak acid or a weak base, and I know what I've ended up with by the shape as well. So, how do I do it? Well, you've met all of the maths that we use to do this already. If I know I've started with a weak acid, then I know how to work out its pH. I know that I can use this little equation, the rearrangement of its equilibrium expression, where the hydronium ion concentration is the square root of the Ka times the acid concentration, and then I can use that H3O plus concentration to find the pH. If this is a strong acid, so it doesn't have that little curvy bit at the start, it just goes along and then suddenly shoots up, then I know just to do the strong acid calculation. The pH is the negative log of the hydronium ion concentration, which is usually the acid concentration. Be careful, if it's sulfuric acid, of course, though, then you'll have to times your concentration by 2 to allow for the 2 hydrogen ions in sulfuric acid. If it was, I'll leave it at that, that's a good example. If it starts at the top and then goes down, then you must have started with a strong or weak base. So what we have to do is use our base calculations, one we've just been working with in the last couple of lessons. If it was a weak base, and you'd know that because it would drop a little bit, then make a buffer region, and then drop dramatically. If it goes along without dropping, and then suddenly drops, it means you started with a strong acid. So we've met these calculations before. Strong base I should have said. For a strong base, it's just two ways to do it. The easiest way is to find a thing called the POH by doing the negative log of the base concentration, assuming that base has only got one hydroxide in it, then going 14 minus that to find the pH. That's the easiest way to do it. And that's what we'd have to do to find section number 2. If, for example, it was 0.1 mole per litre sodium hydroxide, I know that number 2 is a pH of 13.0. If, however, it's a weak base we're working with, we know we have to use Kb and so on, and then substitute in our hydroxide ion concentration to this calculation here. So, you already know the maths to do 1 and 2. All you need to learn now is the stuff on page 197, the general shapes, to know what you started with and what it reacted with. Next term, we'll spend time on 3, 4 and 5 because they take a little bit more time to work through than this. But currently you have the mathematics and the chemistry to be able to do section 1 and section 2, so to give the general shape of a titration curve.